packet switching technology. In this video, we are going to see about packet switching technology. Packet switching is a digital networking communication method that groups all transmitted data, regardless of content, type, or structure, into suitably sized blocks called packets. Packet switching is the dividing of messages into packets before they are sent, transmitting each packet individually and then reassembling them into the original message once all of them have arrived at the intended destination. One fundamental way of differentiating networking technologies is on the basis of the method they use to determine the path between devices over which information will flow. In highly simplified terms, there are two approaches. A path can be set up between the devices in advance, or the data can be sent as individual data elements over a variable path. In this network type, no specific path is used for data transfer. Instead, the data is chopped up into small pieces called packets and sent over the network. The packets can be routed, combined, or fragmented as required to get them to their eventual destination. On the receiving end, the process is reversed. The data is read from the packets and reassembled into the form of the original data. A packet switch network is more analogous to the postal system than it is to the telephone system, though the comparison is not perfect. In a packet switch network, no circuit is set up prior to sending data between devices. Blocks of data, even from the same file or communication, may take any number of paths as it travels from one device to another. Introduction to Internet Protocols. In this video, we are going to see about Internet Protocols. The Internet Protocol is a set of rules governing the format of data sent over the Internet or other network. The Internet Protocol consists of a suite of communication protocols, of which the two best known are Transmission Control Protocol (TCP), Internet Protocol (IP). The Internet Protocol suite not only includes lower layer protocols such as TCP and IP, but it also specifies common applications such as electronic mail, terminal emulation, and file transfer. Internet protocols were first developed in the mid-1970s when the Defense Advanced Research Projects Agency (DARPA) became interested in establishing a packet switch network that would facilitate communication between dissimilar computer systems at research institutions. With the goal of heterogeneous connectivity in mind, DARPA funded research by Stanford University and Bolt, Beranek, and Newman (BBN). The result of this development effort was the Internet Protocol suite, completed in the late 1970s. TCPIP later was included with Berkeley Software Distribution (BSD) Unix and has since become the foundation on which the Internet and the World Wide Web (WWW) are based. Documentation of the Internet protocols, including new or revised protocols and policies, are specified in technical reports called Request for Commands (RFCs), which are published and then reviewed and analyzed by the Internet community. Protocol refinements are published in the new RFCs. To illustrate the scope of the Internet protocols, following figure maps many of the protocols of the Internet Protocol suite and their corresponding OSI layers. Transmission Control Protocol (TCP). In this video, we are going to see about Transmission Control Protocol (TCP). The second transport layer is protocols TCP. TCP, Transmission Control Protocol, is a protocol that works with the Internet Protocol IP to send packets of data between computers over the Internet. TCP establishes a full duplex virtual connection between two endpoints. Each endpoint is defined by an IP address and a TCP port number. The operation of TCP is implemented as a finite state machine. TCP/IP protocols are modeled in 4 layers. TCP operation. The primary purpose of the TCP is to provide reliable, secureable logical circuit or connection service between pairs of processes. To provide this service, Internet communication system requires facilities in the following areas: basic data transfer, reliability, flow control, multiplexing, connections. Basic data transfer. TCP is able to both transmit and receive data streams simultaneously, even though this is opposite to the basic concept of data transmission in many underlying network technologies. The TCP is able to transfer a continuous stream of data in each direction between its users by packaging some number of data into segments for transmission through the Internet system. In general, the TCPs decide when to block and forward data at their own convenience. The data unit transmitted from TCP layer is referred to as a segment. The size of the segments and the timing at which they are sent is generally left to the TCP module. TCP applications request that the data is pushed by instructing the TCP module to deliver all data up to that point without maximum transmission unit (MTU). Reliability. TCP assigns a sequence number to each byte transmitted and expects a positive acknowledgement ACK from the receiving TCP. If the ACK is not received within the timeout interval, the data is then retransmitted. The receiving TCP uses the sequence numbers to rearrange the segments when they arrive out of order and to eliminate duplicate segments. TCP provides reliable communication through a positive acknowledgement system. Flow control. TCP provides a means for the receiver to govern the amount of data sent by the sender. This is achieved by returning a window with every ACK indicating a range of acceptable sequence numbers beyond the last segment successfully received. The window indicates an allowed number of octets that the sender may transmit before receiving further permission. Multiplexing. TCP is able to provide a connection-oriented environment for many simultaneous processes within a single host. TCP uses a set of ports which, when concatenated with the IP address of the host, providing a socket that uniquely identifies an application process anywhere within the Internet. Connections. The reliability and flow control mechanisms described above require that TCPs initialize and maintain certain status information for each data stream. The combination of this information, including sockets, sequence numbers, and window sizes, is called a connection. Each connection is uniquely specified by a pair of sockets identifying its two sides. When two processes wish to communicate, their TCP must first establish a connection, initialize status information on both sides. When the communication is complete, the connection is terminated or closed to free the resources for other users. TCP header. The TCP segment comprises of a header and a variable length data area that ultimately carries application data. TCP header at minimum is 20 bytes long and maximum 60 bytes. Source port 16 bits identifies source port of the application process on the sending device. Destination port 16 bits identifies a destination port of the application process on the receiving device. Sequence number 32 bits. Sequence number of data bytes of a segment in a session. Acknowledgement number 32 bits. When ACK flag is set, this number contains the next sequence number of the data byte expect and works as acknowledgement of the previous data received. Data offset 4 bits. This field contains two meanings. First, it tells the size of TCP header 32-bit words. Secondly, it indicates the offset of data in current packet in the whole TCP segment. Reserved 3 bits. Reserved for future use and all are set 0 by default. Flags 1 bit each. NS nonce some bit is used by explicit congestion notification signaling process. CWR. When a host receives packet with ECE bit set, it sets congestion windows reduced to acknowledge that ECE received. ECE has two meanings. If SYN bit is clear to 0, then ECE means that the packet has its CE, that is congestion experience, bit set. If SYN bit is set to 1, ECE means that the device is ECT capable. URG indicates that urgent pointer field has significant data and should be processed. ACK indicates that acknowledgement field has significance. If ACK is clear to 0, it indicates that packet does not contain any acknowledgement. PSH, when set, it is a request to the receiving station to push data as soon as it comes to the receiving application without buffering it. RST, reset flag, has many features. It is used to refuse an incoming connection. It is used to reject a segment. It is used to restart a connection. SEN. This flag is used to set up a connection between hosts. FIN. This flag is used to release a connection and no more data is exchanged thereafter. Because packets with SYN and FIN flags have sequence numbers, they are processed in correct order. TCP Client-Server Model. TCP is a peer-to-peer connection-oriented protocol. There are no master or subordinate relationships. The applications, however, typically use a client-server model for communications. A server is an application that offers a service to internet users. A client is a requester of a service. An application consists of both a server and a client part, which can run on the same or on different systems. Users invoke the client part of the application, which builds a request for a particular service and sends it to the server part of the application using TCPIP as a transport medium. The server is a program that receives a request, performs the required service, and sends back the results in a reply. Internet Protocol IP. In this video, we are going to see about Internet Protocol IP. The Internet Protocol IP is the primary network protocol by which data is sent from one computer to another on the Internet. Each computer, known as a host, on the Internet has at least one IP address that uniquely identifies it from all other computers on the Internet. The functions of Internet Protocol include defining the Internet addressing schemes, moving data between the network access layer and host-to-host transport layer, performing fragmentation and reassembly of datagrams, routing datagrams to remote hosts. There are currently two versions in Internet Protocol, IPv4 and IPv6. Overview of Internet Protocol version 4. Internet Protocol version 4, that is IPv4, is the fourth version of the IP and a widely used protocol in data communication over different kinds of networks. IPv4 is a connection-less protocol used in packet-switched layer networks such as Ethernet. It provides a logical connection between network devices by providing identification for each device. Internet Protocol version 4 standard that features IP addresses 4 bytes, that is 32 bits in length. IPv4 uses 4 1-byte decimal numbers separated by a dot, that is 192.168.1.1. There are many ways to configure IPv4 with all kinds of devices, including manual and automatic configurations depending on the network type. Overview of Internet Protocol version 6. The Internet Protocol version 6 IPv6 is more advanced and has better features compared to IPv4. It has the capability to provide an infinite number of addresses. IPv6 is replacing IPv4 to accommodate a growing number of networks worldwide and help solve the IP address problems. The newer Internet Protocol version 6 IPv6 standard features addresses 16 bytes, that is 128 bits in length. IPv6 uses hexadecimal numbers that are separated by colons, that is FE80 : D4A8 : 6435 : D2D8 : D9F3B11. IPv4, IPv6. IPv4 address are 32 bits in length. IPv6 address are 128 bits in length. IPv4 address are binary numbers represented in decimals. IPv6 addresses are binary numbers represented in hexadecimals. IPsec supports is only optional. Inbuilt IPsec supports. Fragmentation is done by sender and forwarding routers. Fragmentation is done only by sender. No packets flow identification. Packet flow identification is available within the IPv6 header using the flow label field. Checksum field is available in IPv4 header. No checksum field is in IPv6 header. Options fields are available in IPv4 header. No options fields but IPv6 extension headers are available. Address Resolution Protocol ARP is available to map IPv4 address to MAC address. Address Resolution Protocol ARP is replaced with a function of Neighbor Discovery Protocol NDP. Internet Group Management Protocol IGMP is used to manage multicast group membership. IGMP is replaced with Multicast Listener Discovery MLD messages. Broadcast messages are available. Broadcast messages are not available. Instead, a link local scope all nodes multicast IPv6 address, that is FF02 is equal to 1, is used for broadcast similar functionality. Manual configuration static of IPv4 addresses or DHCP dynamic configuration is required to configure IPv4 addresses. Auto configuration of addresses is available. Router. In this video, we are going to see about router. Routing is the act of moving information across an internetwork from a source to a destination. Along the way, at least one intermediate node typically is encountered. Routing is often contrasted with bridging, which might seem to accomplish precisely the same thing to the casual observer. The primary difference between the two is that bridging occurs at layer 2, that is the link layer of the OSI reference model, whereas routing occurs at layer 3, that is the network layer. This distinction provides routing and bridging with different information to use in the process of moving information from source to destination, so the two functions accomplish their task in different ways. Routing involves two basic activities: determining optimal routing paths, transporting information groups, typically called packets, through an internetwork. In the context of the routing process, the latter of these is referred to as packet switching. Although packet switching is relatively straightforward, path determination can be very complex. Switching algorithms is relatively simple. It is the same for most routing protocols. In most cases, a host determines that it must send a packet to another host. Having acquired a router's address by some means, the source host sends a packet addressed specifically to a router's physical, that is, media access control MAC layer address, this time with a protocol that is network layer address of the destination host. As it examines the packet's destination protocol address, the router determines that it either knows or does not know how to forward the packet to the next hop. If the router does not know how to forward the packet, it typically drops the packet. If the router knows how to forward the packet, however, it changes the destination physical address to that of the next hop and transmits the packet. If the three routers are part of the internet, it will only work this way when both hosts have valid public IP addresses assigned to them. Network Address Translation (NAT). NAT, defined in RFC 1631, allows a host that does not have a valid registered IP address to communicate with other hosts through the internet. The host might be using private addresses or addresses assigned to another organization. In either case, NAT allows these addresses that are not internet ready to continue to be used and still allows communication with hosts across the internet. NAT achieves its goal by using a valid registered IP address to represent the private address to the rest of the internet. The NAT function changes the private IP addresses to publicly registered IP addresses inside each IP packet. The router performing NAT changes the packet's source IP address when leaving the private organization and the destination address in each packet forwarded back into the private network. The NAT feature configured in the router labeled NAT performs the translation. Overloading NAT with port address translation (PAT). Some networks need to have most, if not all, IP hosts reach the internet. If that network uses private IP addresses, the NAT router needs a very large set of registered IP addresses. With static NAT, for each private IP host that needs internet access, users need a publicly registered IP address. Overloading allows NAT to scale to support many clients with only a few public IP addresses. The top part of the figure shows a network with 3 different hosts connecting to a web server using TCP. The bottom half of the figure shows the same network layer in the day with 3 TCP connections from the same client. All 6 connections connect to the server IP address 170.1.1.1 and www port 80, the well-known port for web services. In each case, the server differentiates between the various connections because their combined IP address and port numbers are unique. NAT takes advantage of the fact that the server really doesn't care if it has one connection each to 3 different hosts or 3 connections to a single host IP address. So, to support lots of inside private IP addresses with only a few global, publicly registered IP addresses, NAT overload uses port address translation (PAT). Instead of just translating the IP address, it also translates the port number. NAT overload can use more than 65,000 port numbers, allowing it to scale well without needing very many registered IP addresses in many cases, like in small office or home networks, needing only one. Taking the device called a router by most users apart, it contains different components. IP address. In this video, we are going to learn about IP address. As with any other network layer protocol, the IP addressing scheme is integral to the process of routing IP datagrams through an internetwork. Each IP address has specific components and follows a basic format. These IP addresses can be subdivided and used to create addresses for subnetworks. Each host on a TCPIP network is assigned a unique 32-bit logical address that is divided into two main parts: network number, host number. Network number. The network number identifies a network and must be assigned by the Internet Network Information Center (INTERNIC) if the network is to be a part of the Internet. An Internet Service Provider ISP can obtain blocks of network addresses from the INTERNIC and can itself assign address space as necessary. Host number. The host number identifies a host on a network and is assigned by the local network administrator. IP address format. The 32-bit IP address is grouped 8 bits at a time, separated by dots and represented in decimal format known as dotted decimal notation. Each bit in the octet has a binary weight about 128, 64, 32, 16, 8, 4, 2, 1. The minimum value for an octet is 0 and the maximum value for an octet is 255. An IP address consists of 32 bits. IP address classes. IP addressing supports 5 different address classes: A, B, C, D, and E. Only classes A, B, and C are available for commercial use. The leftmost, that is high-order bits, indicates the network class. In an IP address of 172.31.1.2, for example, the first octet is 172 because 172 falls between 128 and 191. 172.31.1.2 is a Class B address. Email addresses. In this video, we are going to see about email addresses. Email is a message distributed by electronic means from one computer user to one or more recipients via a network. One of the many similarities between email and regular mail is the need for addressing. For a message to be delivered, it is necessary for the sender to specify the recipient and provide a reasonable amount of information to indicate how and where the recipient can be reached. In TCP/IP email, a standard electronic mail address format is used for this, and support is also provided for alternative addressing schemes that may be used in special cases. All communication on an internetwork requires some way of specifying the identity of the intended recipients of the communication. Most application protocols such as the File Transfer Protocol (FTP) and Hypertext Transfer Protocol (HTTP) use conventional TCP/IP contracts, IP addresses, and port numbers to specify the destination of information to be sent. The IP address normally identifies a particular host computer, and the port number indicates a software process or application running on that computer. Email, however, uses a model for communication that differs from most applications. Email is not sent from one machine to another as a file is transferred using FTP. Instead, it is sent from one user to another. This is critical to the operation of the entire system. For one thing, it allows someone to retrieve email that has been sent from any number of different client computers. This allows the recipient to receive email even when traveling. Since email messaging is user-based, the addressing scheme must also user-based. User cannot use conventional IP addresses and ports, so they need a distinct system that specifies two primary pieces of information such as who the user is and where the user is located. These are, of course, analogous to a name and address on a regular mail envelope. The idea of the username is relatively straightforward, but identifying the location of the user is not. In regular mail, an address refers to a physical place. It would have been possible to define email addresses in the same way, that is, to have an email address refer to the user's client machine. However, recall the important characteristic of email delivery. It is indirect and based on the concept of a user's local simple mail transfer protocol (SMTP) server holding received messages until they can be retrieved. The machine that the user employs to access their email may not even routinely be connected to the internet, and it may thus not be easy to identify. And they also want a user to be able to access email from multiple machines. For all these reasons, people want addresses to identify not the user's specific location at any particular time, but the place where the user's permanent mailbox lives on the user's SMTP server, which is permanently connected to the internet. Resource addresses. In this video, we are going to learn about resource addresses. When user using the web, their browser acts as a client program on their behalf. In order to fulfill their request, their browser will contact server and ask for either information or a service of some type. URL, that is Uniform Resource Locator. URLs provide a standard way to specify the exact location and name of just about any internet resource. In general, most URLs have one of two common formats: scheme://hostname/description, scheme:/description. Example 1. http://www.brianadams.com/Brian. This example describes a particular web page on a computer. The URL begins with a name indicating a specific type of resource. The name comes from the protocol used to send and receive such information, Hypertext Transfer Protocol. URLs and hostnames. List of schemes used with URLs are in the below table. Some examples of URLs that contain a hostname: http://www.wendy.com/Wendy, ftp://usenet/usenet/news.answers/alt_tech/pointers.z, telnet://nightmare.internet.com:1701/ URL and port numbers. Each type of internet service has its own specific port number. Within a URL, user only have to specify a port number if it is not the default for that type of service. For example, the default port number for telnet is 23. The following two URLs are equivalent: telnet://locis.loc.gov/telnet://locis.loc.gov:23/. The HTTP service by default uses port 80. Similarly, the Gopher service uses port 70. Path names. Typical hypertext URLs such as http://www.cathouse/humor/text/data.from.well. The user can divide such URLs into three parts: the scheme http:, the hostname in this case //www.cathouse.org/ and the path name in this case cathouse/humor/text/data.from.well. To analyze such a URL, look at each of the paths. The scheme HTTP identifies this resource as being hypertext. The hostname is the name of the computer. The path name shows where on the host the hypertext resource is stored.